Okay. Well, thanks, Al, for that. And I want to explain a bit what's up on the board. The right-hand side you can forget about for a while. The left is a recap of the last minutes of last hour, my second lecture, where I gave an example, or sort of at least indicated that there was an example of this sort, namely of an absolutely irreducible representation of the Galois group of Q unramified outside a single prime P and infinity with a relatively small image. In fact, the smallest image you might imagine, it's the symmetric group on 3 letters sitting in GL2FP, whose splitting field is the Galois field determined by an equation of a cubic equation of the sort written. And if you impose various conditions on deformations of rho bar, you get various deformation rings. The universal one is RD0, that's the with no conditions. And each successive one is a quotient of the previous one. And one of the reasons why I wanted, there are actually 3 reasons why I wanted to write it down. One is that I had written for D3, I had put a GP there. It's really the inertia group at P that I should have put. That's one reason. The other reason is to recall that there are examples which, at least at the very outset, that is, say, the absolutely irreducible representation attached to these examples are very accessible, very amenable representations. And yet, one gets quite a number, just by sort of deformation theory, one gets the assurance of quite a number of deformations of that simple representation. In particular, the winner there, RD3, which is a single ZP. That corresponds to a single representation of the Galois group into GL2 ZP, satisfying condition D3, which is a deformation of rho bar, can be quite interesting. And this was a number of people asked me what are examples of this, and I won't go into detail, but I'll just say, for example, when P is 23 and you have your choice of essentially any determinant. If you take the determinant, which is the 11th power of the cyclotomic character, then the one representation in the GL2 ZP that you get is the representation attached to the modular form of weight 12, delta, for the prime 23. So you get, and similarly for essentially any other determinant, you get rather interesting representations. Okay. Now I would like to remind you of the general setup. So we have pi, a profinite group. And we have rho bar, a representation, no hypotheses for the moment, into GLN K. K is our finite field of characteristic P, as before. And we had mentioned that the deformation problem, I'll write it first that way, the deformation problem for rho bar is nearly representable. That's independent of whether rho bar is absolutely irreducible or not. And specifically, that means that if we take d rho bar, the functor from the category, if you remember, of coefficient rings, residue field always constrained to be K, to the category of sets, sending a coefficient ring to simply the set of deformations. I won't write that. The set of deformations of rho bar to A. This is a nearly representable functor, and one implication of this is that it has a natural tangent space. The tangent space of the representation problem, which I might write T rho bar, is what I really mean is the tangent space of the deformation functor for the representation rho bar, which by definition, you recall, is really d rho bar of the basic first order infinitesimal coefficient ring, that is, say, k brackets epsilon, epsilon squared is 0. This, because it's nearly representable, it is a natural k vector space. And one of the things we sketched a proof of, or sketched the idea of the proof of, is that as a k vector space, it is canonically isomorphic to group cohomology H1 of pi with coefficients in Mn of k meaning the n by n matrices with entries drawn from k, that's the n squared dimensional vector space over k, but viewed now as a pi module via the adjoint action. Let me call this the absolute theory or something. There's even a relative theory. A relative theory would start not with a rho bar, but might start with a deformation of rho bar. Let's call it rho. In fact, a specific homomorphism, rho from pi to gln A, some coefficient ring. And then we could define d rho to be every time we have a coefficient ring A1 with a mapping to A. So this would be from the category of C rings, coefficient rings. Residue field, of course, K, with a given mapping to A to give it sort of old-fashioned algebraic topological terminology. I could call it A augmented. From this category to the category of sets, similarly to the set of deformations of rho to A1. Now, just as the absolute theory has a vector space attached to it, so does this relative theory. That is to say, I could define, let's start here, I could define T rho just by definition to be d rho of the A augmented coefficient ring, which consists in adjoining to A epsilon with the similar requirement on epsilon that we had before, namely epsilon squared equals 0. And this, by the same argument, really, that we gave for showing that d rho bar of k brackets epsilon is a vector space, this is naturally an A module. So the relative theory has A modules, and the same proof gives that this is isomorphic to H1 with its natural A module structure is isomorphic to H1 of pi with coefficients now in what you might guess, where this is again the adjoint action via no longer rho bar, but via rho. I'm going to say pi maps to glna by rho, and then glna acts on mna by conjugation. Okay. Gee. One day, and I forget the board regimen. Okay. What I want to spend some time in this lecture is talking a bit about something that's quite important, I think will be quite important for the later lectures, talking a bit about, let me call it conditions on deformations. And by way of example, there's a condition that I've already put up on the board and referred to. I want to describe this in some detail now. The fixed determinant condition. Fix the determinant. Now, what do I mean by this? So let's suppose we have a representation such as above. And suppose we're given now a character, a continuous character. I'll call it delta. One can be more general than this, but this will certainly give the idea and be, in fact, the most usual example. Suppose we have a character to the topological group ZP star. I want to say what I mean by a representation of GLNA having determinant determinant delta. So what could I possibly mean by that? Well, I have a representation pi to GLNA. Of course, I can take its determinant, and that goes to A star. Of course, delta goes to ZP star, so there's a sort of disparity there. But any of my coefficient rings contains the identity element, and so therefore admits a homomorphism from Z to it, but P is topologically nilpotent. So all of my coefficient rings really are canonically ZP algebras. And so we have a canonical homomorphism which induces, I'll call it IA if you wish, which induces a homomorphism on units. And then I'll say that rho has, I'll put quotes around it because it's a little funny, determinant delta. If this diagram is commutative, let us say if IA composed with a delta is the determinant of rho. Now that's a condition. We can impose that on our functor. That is to say, we can ask, well, we certainly can ask that a deformation have determinant delta. So we could write a d rho bar of delta of any A to be the subset of representations, those with determinant, quotes around it if you wish, delta. This doesn't make any sense really unless rho bar itself has determinant delta. If rho bar has determinant delta, then we have a nice functor. I could call it, well, I've called it d rho bar delta from our category of C rings, coefficient rings, to sets. It is a functor of the sort that we've been dealing with. That is to say, if we take the coefficient ring, which is the residue field itself, it is a single element, a singleton. Namely, the only element in it is rho bar having determinant delta. Now, here's a fact, a theorem, which I want to sort of view from a slightly different light later on. So let me just sort of, whoa. Okay, so let me just sort of put it in a box. You can prove it, not too hard. This subfunctor, it's a subfunctor of d rho bar, is always nearly representable. And it's, in fact, representable if rho bar is absolutely irreducible. Well, it being nearly representable, means, for example, that it has a tangent space, and so we should be able to compute the tangent space. So let me try to do that. So perhaps I'll call it the tangent space of rho bar with fixed determinant delta. Of course, this is just a d rho bar delta of k brackets epsilon. And that's, by definition, a subspace of the tangent space of rho bar. And the tangent space of rho bar is canonically isomorphic to h1 of pi with coefficients in mn of k. And so, therefore, whatever this is, it is isomorphic to some subspace of this cohomology group. I mean, provisionally, I might call it h1 sub little delta of pi mn of k, whatever it is. It's some subspace of cohomology. And the lemma is that this is, in fact, exactly the following subspace. Namely, you take h1 of pi with coefficients in the natural pi submodule of mn of k, consisting in those n by n matrices with coefficients in k which have trace 0. So this is trace 0 matrices. Of course, that is pi stable and represents a k subvector space, and that's the answer. And just for fun, because it is in some way indicative, it's the easiest of the local calculations that one, in fact, in the later theory has to make on mass. I want to do it a bit. For that, I have to remind you already of how we computed this isomorphism, that is, say, how we computed d rho bar of k brackets epsilon. We did it by a little diagram of groups. We had our representation rho bar. There was a natural injection of k in k brackets epsilon, and so that gives us a natural lifting of that representation. And now if we took any other lifting rho, we defined the difference cocycle for elements in pi to be simply the ratio, a rho of g times rho bar of g inverse, which lies in the kernel, and the kernel is 1 plus epsilon mn of k. That was from last time. Of course, this is to be viewed as a group. It's a group under multiplication, so I'll put mult up here. And if you want the additive version of it, we just divest an element of its 1 and its epsilon, and we get the just additive group mn of k, that isomorphism being a log or an exponential, depending upon which way you're going. And now let's compute what happens when we apply the determinant to this. Well, here we have the determinant of rho over the determinant of rho bar of g. And this is contained in the determinant of this, which is in 1 plus epsilon k, which is contained in the units of k brackets epsilon. Of course, we have a similar log or exponential here, which replaces this by k. And the whole point of this little exercise is to notice that if you complete the diagram by putting a trace here, this is commutative. Since it's commutative, and since rho bar has determinant delta and rho has determinant delta, this image is 1. So when you go by the logarithm, you get 0 here. That is to say, all the cocycles we've ever constructed in the isomorphism already take their values in the traceless matrices. And that's the essence of the calculation. You can read that in the reverse manner. If you have a cocycle that takes its value in the traceless matrices, the determinant of rho is delta in this quotation mark sense. Okay. Okay, why did I sort of go through this in such detail? Well, first because it's I think it's slightly revealing that we have a sort of a simple condition, and the condition is interpreted in terms of Galois cohomology, and that is in some sense indicative of what happens in general. Now, in trying to consider the various panoply, I called it a bestiary in the notes, bestiary of conditions that you might impose on a representation, each one with its little theory, it occurred to me that for these lectures, maybe one should try to systematize the bookkeeping some. And so I'm going to define, and this seems to help the lecture a bit, maybe. I'm going to define what I'll mean by a condition. A condition in general. I've just given you a fixed determinant condition, but I want to define a condition on the deformation problem for rho. Rho bar. Well, the deformation problem for rho bar is packaged by its functor, d rho bar. And a condition will be just a subfunctor. So a condition is a subfunctor d. So that is, say, for every coefficient ring, we have a subset of the deformations of rho bar to that coefficient ring, that subset being the ones deemed to have the condition d, with the obvious requirement that d of k not be empty. That is to say, it has to consist then of the single element rho bar. So rho bar satisfies the condition. And the requirement, so that's the first requirement. The second requirement is that this inclusion of functors, and this seems to be the right thing to ask, that it be relatively representable. Now, that's why I prepared that other board, because to define relatively representable, you have to make a diagram with an incredible number of A, B, C's, and D's. And in big chalk, it's sort of, okay. So actually, I'm beginning to like this big. You know, maybe it might become an addiction. I might crave bigger and bigger chalk. And then sort of get lost in an opaque cloud of like a Michelangelo wannabe or something. Okay. Okay. What does it mean to be relatively representable? A subfunctor is relatively representable. Script D in Roman D is relatively representable if, remember from this previous lecture, that representability, or at least what I call the earmark of representability, was Meyer v. Torres, namely that for every diagram ABC of coefficient rings, the induced mapping, that upper horizontal arrow, if capital D was representable, that induced mapping would always be an isomorphism. Well, capital D may not be representable, as will be the case when one takes global representations and restricts to decomposition groups. Nevertheless, we want script D to be no less representable than capital D. That is to say, we want that for every diagram, to get an element in script D of A cross B over C, all you have to do is take an element in Roman D and map it to the upper right-hand corner of the diagram and see, does it come from script D? If it does, then then it should be in script D. So what does it mean to be Cartesian? We'll say that A, B, different A's and B's and C's, C, D is Cartesian. If to give an element an A, all you have to do is give a pair of elements B and D in B and D respectively, which map to the same element in C. So an element alpha and A correspond precisely to pairs B, C, B and D, such that B and D map to the same element in C. I'm going to erase this. One implication of another way of saying it is, well, I think I'll say it simply by sort of pointing to the diagram once more, and then leave it at that. To give an element here, it suffices to give an element here and an element here, which map to the same element there. Okay. Now, one reason for sort of introducing this notion is that if you go through all of the local conditions that occur in Weil's paper, the determinant condition, for example, they're all relatively representable. They are all conditions in this sense. And if two functors are relatively representable this way, if D in D is relatively representable, then D satisfies any number, any one of the Schlesinger criterion, I equals 1, 2, 3, or 4, implies that script D also does. That's easy to see using the definition. In fact, it's immediate. In particular, relatively representable deserves its name in the sense that if D is representable and script D and D is relatively representable, then script D is. And if D is nearly representable, then script D also is. In particular, every condition is nearly representable and representable if rho bar is absolutely irreducible. So this box is not only true for the determinant condition, but every condition that we'll ever encounter. Suppose we have a condition then on D rho bar. Suppose script D is a condition. Whenever we have such, we have a calculation to make, which of course I will not make except for the one I've done. Namely, we can take the tangent space of rho bar, which is the tangent space of D rho bar. We can view it as isomorphic by our lemma to h1 of pi with coefficients in mn of k. we can consider the subtangent space of our condition, and our condition certainly has a subtangent space because it's nearly representable. And that will be isomorphic to some subvector space of Galois cohomology. And to keep with Weil's notation, perhaps I'll call it H sub d, depending upon the condition, pi mn of k. Of course, this is just a name. I should emphasize that each time we have a condition, we have a calculation to make, namely to actually figure out what that corresponds to in Galois cohomology. Okay. Now, what I would like to do is pass to the global situation. So I want to take for my pi GQS. The Galois group of Q, of the maximal extension of Q unramified outside S. I take rho bar, any representation, continuous representation of GLN of K. I would like to impose, sort of following the format of what will be useful later, I would like to impose a system of conditions. So the first condition will be fix a character. I'll call it delta from GQS to ZP star. And we're going to impose the condition that our representations, our deformations, will have determinant in that sense that I introduced, delta. And two, fix a condition on each of the local deformation problems for each of the decomposition groups GL, where L is in S. So if GL is the decomposition group for the prime L, and if I let rho bar sub L be the restriction of rho bar to the decomposition group at L, I want to fix a condition, I'll call it D sub L, in the deformation problem for, not for the global representation, but for the local representation rho bar for each L in S. And this whole data is going to define for me a global condition, call it script D. Namely, I can define a, I'll just call it a D deformation of my global representation rho bar to be, I won't write it down, but I hope it's, well, it's clear what I want it to be. I want it to be, I will write it down. So D of A is first a deformation of our rho bar, which has determinant delta, but which has the property that every time I restrict my deformation of rho bar to rho bar sub L for each L and S, so I could consider it mapping to the product of the sets d rho bar sub L of A for L and S, I want it to actually come from the selected subset coming from considering each of the conditions in turn and taking their product. In other words, I want this diagram to be Cartesian. I want it, and it's an easy lemma. Well, I define D this way. D is a functor, and it's an easy lemma that D is again a condition. That is, say, D contained in D rho bar is relatively representable. Let's interpret this in terms of tangent spaces, which is my charge. Let's apply this to the study of the tangent space of the, by the way, I should put a capital D here. Apply this to the tangent space of the now nearly representable functor script D. It's nearly representable because D rho bar is nearly representable, and D in D rho bar is relatively representable. So the tangent space in D then obeys such a beautiful Cartesian diagram. That is to say, it is the subspace of the tangent space of rho bar subject to the condition delta. That is to say, if I apply this to this diagram with A equals K brackets epsilon, I simply read that this is contained in H1 of G, Q, S with coefficients in the traceless matrices, n by n matrices of K. If I go down here with A equals K brackets epsilon, I get that this is the product for L in S of H1 of GL with coefficients in the n by n matrices. I put no determinant condition over there. And this becomes what I previously called H1 DL GL with coefficients in Mn of K for L and S. And this gives a determination of the tangent space of the deformation problem with condition D as the subspace of the cohomology, the global cohomology, which, when restricted to each local prime in turn corresponding to the ramified primes, satisfies the local condition that we've imposed. It's sort of a perfect example of the type of Selmer group setups that one sees in other aspects of the subject, and one is, I assume we'll see a lot more in the lectures to come. Well, what is this tangent space? This tangent space, in the special case where rho bar is absolutely irreducible, we actually have an interpretation for it, namely if rho bar then rho bar is absolutely irreducible, so its deformation problem is representable, and therefore the condition D is representable. What does that mean? That means that we have a universal ring, I might call it R of rho bar, the universal deformation ring as we've introduced in the first lecture, and Henrik Lenstra proved exists. But also, so is script D, and so it too has a universal ring attached, which is a quotient of R. We'll call it R sub D. Maybe I'll call it R of rho bar sub D also, which is universal for D deformations. in which case we can interpret this tangent space as the Zariski tangent space of this ring, as we did in the previous lecture. So we can replace this, if we so wish, by the tangent space of RD. In particular, the way in which to understand the complete local ring RD is to sort of make this Selmer group type calculation and sort of see what you get. That's for the absolute theory. Let's, in some way, that sets the pattern. Nevertheless, there are some surprises with the not surprises, but sort of slight differences with the relative theory, and it's the relative theory that we're sort of particularly charged to explain, and so let me sort of move to the relative theory. Okay, for this relative theory, I want to talk about Kaler differentials for 1 minute at least. So Kaler differentials. And I'll try to draw it down as much as possible. Now, what is a Kaler, the module of Kaler differentials? R can be any coefficient ring here. That's my setup. And I'm going to sort of describe a certain module. I'll construct, in fact, a certain module, which is an R module. And let's say, suppose you're trying to go to Boston University by the T, and you're in a conversation at Park Street, and you're supposed to explain what omega r is, so as not to get too distracted so you don't take line C rather than line B when you make the change. You have to sort of just say it in 2 words. Okay, so what's, well, at least a phrase. I guess my phrase would be it's the largest piece of information about the R module that can honestly be considered first-order deformational information. Okay. But that's not, that may not be, that's okay for changes on the T, but okay. So let me construct it first. I'm going to take the tensor product of R with itself, and here, rather than overburden this big chalk blackboard with extra hypotheses, let me suppose that K is FP. This is totally unnecessary, just sort of save some chalk, really. So when tensor product means R is a ZP module, ZP algebra, in fact, is R. So tensor product, and I will tend not to, well, I won't introduce the tensor product too much, but if it's unlabeled, it will mean over ZP. Okay, there's a natural mapping of this to R, namely product. From the geometric level, if one takes spec R, and it's sort of like the diagonal in the product of space with itself. We can take the kernel I, which is the kernel of this mapping. So if I call the mapping alpha, this would be kernel of alpha. And so this is the ideal defining the diagonal in the product. Now, what is I? I is quite naturally an R tensor. To be absolutely within my category, I should take the completed tensor product because all my C rings are completed, so it sort of hardly matters, but I'm going to do that. So it's an R tensor R module. That's what I is because it's an ideal in R tensor R. So I can pass to I modulo I times I, and that becomes an R tensor R mod I module. But R tensor R mod I is just by this very diagram R again. And that's the construction of omega R. Omega R is this R module. In some sense, it's the co-normal bundle of the diagonal of the product. It's the universal module for derivations from R. What? My R's are coefficient rings with finite. Yeah. Okay. Why is this? Why do I say that it's sort of the maximum first order? Well, why does it contain any first order information? Well, you can consider, for example, Hom of omega R as an R module into the residue field K itself, viewed as R module. And I leave it to you to check that this is nothing more than the Zariski tangent space that we defined. And in fact, you can, once you sort of work it out, you'll see the M mod P M squared coming up fairly easily. It's the Zariski tangent space of ring R. So, but this is just Hom into something quite small, the residue field. It has much more information. It may have much more information than the very residue field. It's in terms of omega R that I want to introduce the relative theory. So for that, I will write down a Cartesian diagram that is going to look very, very much like either of these. But let's start with, we may as well do this in the sort of special case that we're dealing with, so I'll call it GQS. We assume we have our representation into GLNK. I'm going to assume it's absolutely irreducible, and I'm going to let D be a condition of the sort that we had introduced. And I want to, since I have the relative theory, I want to have already chosen a lifting of rho bar to a GLN-A, where A is a specific coefficient ring. So fix all that. Well, by our sort of previous discussion, if D is a condition, rho bar is absolutely reducible, D is representable, and so there's the universal D-deformation ring, which we can call RD. There's assuming that rho is a D-deformation. And so that means that we have a definite unique homomorphism from RD to the coefficient ring that induces rho. In particular, I want to think of it this way. I want to think of A as being an RD algebra, which I can. If I have a homomorphism to it, it's an RD algebra. Okay. I also want to specialize to a specific, they're going to specialize to two cases, and the first is A is Artinian. Equivalently, under our situation, A is finite. And this is the absolute version, and we're now going to produce the relative version. The relative version goes like this. We want to consider Hom over RD of the RD module omega RD into A viewed as RD module. It's an RD algebra. Perhaps I'll write RD modules. Yeah. Is contained in H1 with of G, Q, S with coefficients in M, N of A now with a 0 maps to the product for L and S of H1 of GL with coefficients in M and A. Same thing, I mean, as before. Maps to the product, L and S, of the part of the cohomology that satisfies the local condition at L, GL, M and A. And the proposition, in fact, I might call it proposition 1. There would be 3 versions if I have the time, but I might not sort of get to labeling all 3, is that this is Cartesian. As a diagram, meaning that to produce a homomorphism of omega r d to A, you need only consider a cohomology class, a global one, which, when restricted to each of the local cohomologies obtained by replacing GQS by the appropriate decomposition group, you lie in the selected subspace. And the cohomology, of course, since we have a fixed determinant condition, actually lies in the traceless matrices of MNMA. As I said, I want to give at least another version so as to make it make the connection with what I imagine to be things that people might be dealing with in a later lecture. And one tends not to deal with the Artinian case. One tends more to deal with the case where A is free over ZP, in which case this diagram looks a little different. What you do is you take, in some sense, the limit of these diagrams where you replace A by A mod P to the N. And when you do that, you get a similarly Cartesian diagram where each of these coefficients are tensored with QP mod ZP, otherwise exactly the same. Should I do that? I will call it proposition 2. Yeah, why don't I just display it? So if A is free over what? Could you define those maps? Which ones? Like the left vertical. Yes. You want me to define those maps? No. No. Oh, yeah, they're there. The way in which you define it is, well, I'll define it if you want. Yeah. No, they're there. See, the condition that, the condition D includes a local condition DL for each L. And on the local level, what that means is that it's going to be contained in the local version of H1DL if you sort of replace it by local. In other words, what you do is you You know what I want to do? I want to. I've got 3 minutes, and I would like to just sort of make the connection with p mod p squared. But the answer is it's simply rigged, and you just do it on the local level. The local functor is sort of given by. Of course, I haven't proved even the proposition. Even after I define the maps, you have to actually prove this proposition, and it is contained. Well, I guess in my paper with Tilloween, we prove a version of it, and but it's the direct generalization of the relative case, which is quite immediate. I mean, direct generalization of the absolute case, which is quite immediate. So proposition 2 is under the hypothesis that A is free over ZP, it's the same diagram except you replace everything by QP tensor ZP. So it HOM of over RD, omega RD, into A tensor QP mod ZP. It's contained in H1 of GQS, Mn of A 0 tensor QP mod ZP. Goes to the product over L and S of H1 of GL Mn of A tensor QP mod ZP. And again, by virtue of the fact that it satisfies the local condition DL at each L, it's contained in the subspace, which is the product L and S, H1 DL, GL, Mn of A, tensor QP mod ZP. Now, the third version of it, which you will find, I think, referred to quite often, doesn't have Kaler differentials at all, but let me imagine that we're in the simplest situation, namely where A is, usually it's applied when A is a discrete valuation ring O, as in some of the previous talks, but I'm going to take the simplest case so as not to tensor things with O. I'll take A to be ZP. When A is ZP, the homomorphism from RD to A, of course, is surjective. And the kernel is a prime ideal, because A, ZP is a discrete valuation ring. So if I let P be that kernel, and if I make use of the fact, which you can compute easily, that in the case that ADP, omega RD tensor over RD with A, which is ZP, is P mod P squared. If you remember, omega is defined by I mod I squared, and that's. And if I make use of the fact that this is also, can be thought of as HOM over A of omega RD tensored over RD with A into A tensor QP mod ZP. then I have a third form of the proposition, which perhaps I will spend a minute writing. A is ZP of P mod P squared into QP mod ZP. That's that, as contained in the cohomology of GQS with coefficients in Mn of ZP upper 0 tensor QP mod ZP. Goes to the product for L and S, H1 of GL, Mn of ZP, 0 tensor QP mod ZP. Goes to the product for L and S of H1 DL, GL, Mn of ZP, tensor QP mod ZP. That this is Cartesian. In particular, the size of this module is regulated by the cohomology subject to these specific local conditions. Each local condition has to be computed. Now, one of the things I should say is that every one of these local conditions, cohomologies, that come up in at least in the paper of Wiles, every one except for one local condition is fairly straightforward Galois cohomology. That is to say, we can easily sort of first guess and then prove what the local condition is for any DL that occurs in the bestiary of conditions that are dealt with, except for one case, which is the finite flat case, where one has to make use of somewhat more sophisticated means. And that, I think, is going to be treated in the later lectures. Okay, thank you.